Here we go. Today we're talking about exponential functions, specifically those related to compounding interest. So, one thing that's really important before we start about compounding interest, specifically continuously compounding, is we need to understand the number e. E is the natural base, right? It's like the natural log is log base e. This limit definition is how we get it. But really, it's just this infinite series. The sum of this infinite series ends up being about 2.71828. And that's a number that goes on forever and ever, similar to pi. So the natural exponential function is going to look like this, e to the x. Notice we have a horizontal asymptote here at 0, right? It'll never cross 0, but it get really, really close. And that's because there's nothing we can plug into x to make this function equal to 0, right? We also can't make it negative because if we put in a negative exponent, it just makes it really, really small, right? Makes it into a fraction. Another fun fact, the slope of the tangent line at x equals 0, so that means it just like touches, bounces, just that one singular point. The slope of this line is 1. But one really important thing to note about our exponential here is that notice how we're starting so small on the left, right? We're growing really, really, really small, and then all of a sudden it takes off. That's the important thing to know when we're thinking about exponentials. We want to know what this graph looks like. Okay, now to the important thing, compounding interest. So compounding interest, we have two different formulas. We've got an annual formula, which means it's like how many times does it compound per year, and then the continuous formula, A equals P times E to the RT. I call it PERT. And that's when it's compounding continuously. So you can see what all these different variables mean. I'll run through the formulas, but first let's talk about what compounding actually is. So compounding means I have a certain amount of money in an account, let's say $1,000, and I earn 10% interest. Okay, so I earn $10. Compounding means instead of just like, okay, you get that money, it's out of the account, I'm going to take that $10, keep it in the account, and your account's going to grow. Well, now if I have $1,010 and I have 10% interest on that, well, that's even more money than my $10. And so it keeps dumping on, and the amount of money you have is going to grow because of that compounding, right? The more money you have in your account, the more money you'll get back from the interest. Well, then that cycle continues and continues. So according to this, well, why wouldn't you want to compound continuously, right? The more you compound, the more money goes onto your account, and the more it's going to grow. That kind of makes compounding continuous confusing because a lot of people think like, oh, well, why don't we just compound continuously? It's going to shoot to infinity. I'm going to be a gajillionaire. That's not quite how that works. Because when we're compounding continuously, it's that 10% interest. But since it's continuous, you're just getting an itty bit amount of money. And then that's growing and that's growing. So it's not growing as fast as the word continuously might, lead you to believe. But compounding continuously is going to give you more money in the end. That's confusing. I know. We'll talk about more later. I promise. Let's get into being able to calculate these things. So T, what's important about this one is that it's in years. P, the principal, that's like how much money you start with. So think, right, I wrote initial right here. A is the account balance, so how much you have after a certain amount of time in years. And then R is the rate. We always want this to be as a decimal. Interest rates, they're going to say like, oh, it's 11%, it's 4%. Always write this as a decimal. And then specific to the annual formula, we got N, and that's the number of times it's compounded a year. So common compounding is like monthly. So you'd put the number 12 in because 12 times a year is once every month. Quarterly, quarter, 4 quarters to make $1. Quarterly means n equals 4. It's going to compound 4 times a year. Those are the ones that are the most common. With the continuous formula, main thing is E is a constant. It is not a variable. Sometimes that messes people up. Let's put these formulas into action. So Mr. Bourne invested $500,000 into a savings account at a local bank. It's a lot of money. The account has a 3% interest rate. If Mr. Bourne does not make any other deposits or withdrawals, what is his balance after 11 years if the interest is compounded? So we have two different scenarios here. One's where we're being compounded monthly, and the other one is continuously. We're going to see what happens to Mr. Bourne's money. So he invested this much. So that's initial. The initial amount of money he puts in. So that is our principal. 500, 2,000. Then in our parentheses, we got 1 plus. R is the rate, but as a decimal. So an interest rate of 3%, 0.03, over N, the number of times it's being compounded. That comes from this right here. We're going to compound monthly. So 12 times a year. Lastly, we need to know how long in time it's going to be. So 11 years before he looks at his account again or does anything to it. So compounding 12 times a year for 11 years. And that's going to give us our account total. So when you go, you plug this in your calculator, you're careful about making sure that both of these are being multiplied in as an exponent. Plug it in. And we get 695,197.713, but we're doing this in money, so we're going to leave it like so. So $695,197.71. That's how much money he got just from putting his $500,000 into this account and just letting the interest do its thing. Pretty neat. When you compound continuously, let's see how it changes. So compounding continuously, we still have that initial principal of 500,000 times E to the R, same interest rate of 0.03, time in years, well, that's going to be 11 years. When we go and plug this one into our calculator, the E to the X button is right above our natural log button. We type this in and we get 695,484.06. So $695,484.06. Compounding continuously, notice, definitely got more money from that, right? The more often you compound, the more money you'll get in the end. Important thing to remember. All right, this one, sometimes you're going to have to solve for different things in an equation. This one specifically, we are looking at how much time is required. So let's go through figuring out how to do that. So it says $4,000 is deposited in a fund at an annual percentage rate of 11%. That's pretty big. Find the time required for the investment to double if the interest is compounded continuously. All right, so continuously, that means we're working with the A equals PERT. We know that we're starting with $4,000. We know that the rate is going to be 11%, which is 0.11. And then time is what we're solving for. That's what we don't know. So since we're solving for time, we need to make sure we keep this as an equation, right? Because we're going to use A. But looking at this, we don't necessarily know what's in our account. So we have to use those hidden clue words. We look at this double. Well, if what's in our account has doubled, that means instead of $4,000, we now have $8,000. So initial goes next to the E. The doubled amount goes on the other side of the equal sign. We need to solve for T. first things first, you have to get our exponential e to the 0.11t. That has to be isolated. So to do that, we're going to take this, divide both sides by 4,000. We're left with 2 equals e to the 0.11t. Move this over, show you why. I need to get the t out of the exponent. That's what we're trying to solve for, but it's in the to the power. So the only way to get rid of that exponential, to bring the exponent down, is we have to do the inverse. The opposite of e to the whatever power is the natural log. So, right, just like multiplication has division, addition has subtraction, exponential has our log. Whatever we do to one side, we have to do to the other. So this isn't multiplication, this is just us like plugging in what's happening in the function. The ln and e are inverse operations, so that means that 0.11 is going to be dropped down. And then ln of 2, we could do that in our calculator, get a really long decimal, we're just going to leave it for now. Final thing, solve for t, we've got to divide by 0.11 on both sides. And we get ln of 2 divided by 0.11 equals t. This is technically the exact answer, but a lot of times I don't know what exactly that means for time, how much time that's going to take. So when we go plug this into our calculator, we'll get that our time is about 6.3. And remember, t is always in years. So just by dropping this $4,000 into this account, 11% interest compounded continuously, it's going to take 6.3 years, not even touching it at all, for it to double. Pretty neat.